Hello folks, and welcome to Rational Science. Today we're going to be talking about phonons and whether they're rational. Okay? And so here's the question of the day that I want to try to answer for you to keep track and follow my train of thought. Okay? Question of the day, are pseudo and quasi particles rational? And there you see the criteria for irrationality that I'm going to use. Okay? And it's if you reify a concept, you turn it into something concrete and think you're moving something real around when all you're moving is an abstract concept, okay, like love. And I guess you turn it into a heart and you begin to move the heart around and you're saying, oh, I'm moving love. No, you're moving a heart. That's not love. Love is something else, and that sort of thing, okay? And there are other criteria, not having definitions or using them inconsistently, okay? The theory doesn't follow from the assumptions, etc., etc. The main one's going to be that first one, reifying concepts, turning a concept into a physical object, and then pretending to move it around. Okay, let's go with this next one here. Okay, so what we were doing these last couple weeks is we're looking at how the world originated. Okay, so let's do a little review of that because it does lead into what the subject of today. And the official version today out there is that there was a big bang, an explosion some 13.8, 14 billion years ago, and it grew into what you see there. We're at the right-hand side of that spilled cup, a cup that's tilted on the ground, okay, so what you see there are the time slices as you look at it, okay, as you look at this whole thing, and we're at the right at the edge there of time, which is on the right hand side. Okay, so this is how they visualize, the mathematicians visualize, this is the explanation they give, the theory they have for how the universe came to be. In other words, there was some kind of explosion billions of years ago, and that evolved through all these little intermediate steps that I covered the other day. And we ended up where we are today, which is, the universe we have today with galaxies and stars and atoms and so on. They claim it didn't start like that. Those atoms were manufactured, then we went from there to galaxies and eventually to stars and etc. Okay, so just have to look at the previous videos to get an idea of what these people are talking about. Okay, I covered a couple of people who proposed how the universe came into be, how matter came into be from absolutely nothing. Okay, so that was the deal. Because in the case of Christianity, you have God, making the universe. He's eternal. But in the case of mathematical physics, they get rid of God and they say the universe kind of self-kick-started. And you say, how did it do that? Please give me an explanation for how matter came into existence by itself and from nothing. Tricky, isn't it? Okay, so this is what these two gentlemen, Stephen Hawking, who's no longer around with us, and Neil Turok, his understudy, I guess. I covered those the other day. Again, I looked at Astronomy Magazine, an article that was written about them where they testified essentially in 1999 about how the universe got started. And that's what we have today. So nothing has changed in 20 years, okay? And essentially, here's the essence of it, in other words, okay? You've got that cone there, which is what you saw a minute ago, the Big Bang expanding, etc. And time goes along the edge of the cone. And the input that Hawking and Turok did, put into this picture, is that it didn't really start out at a point, okay, at a dot. It started on a little curve there, as you can see on the right-hand side there. There's a little curve, and they call it the P instanton. Okay, P because they say this is what it more or less looks like, and instanton is this pseudo quasi particle from which everything started. And you say, what do you mean by that? How can something start from nothing? And the way they explained it is that time does not go along the edge of the cone. In the case of the instanton, okay, time is merged with space, and both of them go around as a circle all the way down to the bottom of the instanton. Okay? And the instanton is rounded, so no matter how small you make your circle, if that circle represents space and time, you have no origin to space and time because a circle has no beginning or end. It just goes around and around and around in circles like these people did. Okay, so that's their notion. Of course, they don't have a physical interpretation for that. Really, what they do is they say, well, we have a mathematical equation that describes this. And the notion behind it is that there is no beginning to time because it's merged with space, and it's represented by a circle which has no beginning or end. And so those are the notions. That's how they introduce the beginning of the universe from nothing. They call that nothing the instanton, okay? And the reporter asked him, well, where did the instanton come from? And it says, and the answer, that's an irrational question. You can't ask that question. It's unscientific. Okay, so the buck stopped there. Okay, and they said it's just the laws of the universe that created the instanton. So where did the laws come from? They said, well, we don't know how to create something from nothing. That was their answer. So after all that work, we understood nothing. We have no notion of how something can come from nothing. It's just a lot of blah, 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 and mathematical equations, and we have no idea what the mechanism is. Okay, so that's the issue. Okay, here's the another fellow who did not agree with him, does not agree, he's still alive, Andrei Lindy, and he's Russian. He works at Stanford University. He's a teacher there, or a professor. And he said, he doesn't know how to create something from nothing. He thinks that's religion. Sounds to him like religion. No, it's not really religion. What it is an irrational explanation, because you have no way of rationalizing it. You have no way of visualizing the mechanism. That's why it's an irrational explanation. It becomes religion when you believe that that's what happened. When you take that as proof, or to you that's the way things happen. Then it becomes a religion, because now you believe that that's how it happened. But as long as you just explain it, I can explain what these people did, doesn't mean I believe in it. I'm just explaining I'm just giving you an irrational explanation. And that's essentially what he's saying. He's saying that sounds a lot like an irrational explanation. What does he propose instead? He proposes the multiverse. He says, well, there are all these universes popping in and out of existence, I guess, like bubbles out there. And that's his version of how the universe started. Ours is just one of the little universes out there that, got kick-started somehow. And again, he doesn't explain it because he doesn't claim to have an explanation of something from nothing. So he eludes that question altogether. Okay, this is just in case for reference, this is Christianity's version, which is God waving his magic wand, according to the Bible, and just saying abracadabra, and the universe came to be. And God is assumed to be eternal. Okay, so God's always been around, so no one created him, and so we have eternity creating the temporal world. Okay, I guess you could say. Okay, so let's proceed here. This is my summary of what these people said. Again, I'm just reviewing this. Okay, the instanton is a pseudo particle. Okay, what is a pseudo particle is a concept that is halfway in the process of morphing into a particle. Okay, it's not yet a particle. It's a pseudo, but it's on its way. It's halfway between being, it's in a limbo, somewhere between being and not. That's what they're trying to tell you. Actually, it's an equation. That's all it is. That they treat as a particle, and it's got to do with that word particle, because they use that word, but they don't mean it. They don't mean what we mean in physics by a particle. You mean like a corpuscle, a little grain of sand, a little bead, tiny bead. That's a particle. We understand that. We all understand that. But when they say, look, it's a particle, and you say, oh, what do you mean by a particle? Well, it's an equation. It's a probability function or wave or whatever. And then you start wondering, you're saying, what do you mean? You call that a particle? Why don't you call it a probability wave or whatever, an equation? Just call it an equation. A description, mathematical description. That's what it is. That's not a particle. But that's where they suggest, they insinuate that they're giving you a physical interpretation because they use the word particle. When you dig in there, you find out that the word particle is not what you thought was a particle. Okay. Same with spin, by the way. They use the word spin. They talk about spinning electrons, etc., etc. And you say, okay, I understand all that. Turns out they weren't talking about an electron, and they were not talking about spin, like when you spin a top. No, spin is something else, which they have not been able to define now in countless years. Okay, so spin is not spin. So particles are not particles, spins are not spins. You got to be very careful with the language in quantum mechanics. Okay, the instanton is a solution to an equation. That's what an instanton is. Just a solution. It's a number. Okay, so That's what an instanton is, okay? How a solution to an equation becomes a particle is a mystery that no one will ever be able to explain in a rational manner, okay? So this so-called instanton, pseudo, or quasi particle, no, they cannot explain it. They cannot rationalize it, okay? But you must pray to the instanton because quantum says that it's the God particle. It's not the Higgs, the God particle. The God particle is the instanton because that's when from where the universe arose, when it was born. Father Universe was born in that little egg, that little pea called the instanton, okay? Which is an equation. That's all it is, a solution, whatever. Everything started out at the Big Bang, not at the Big Bang, but at the instanton. Big Bang is frame number 2 in the film. That's when the explosion occurs. But before that, frame number 1, these were proposing was the instanton, and that's essentially what all these mathematicians believe, okay? That they vouch for the instanton because they use this term. Okay, so it's not like nobody believes in this. No, they do, but that's not what they tell the folks out there, because if they say to the common man that everything started from nothing and here's the little pea called the instanton, people are going to say, well, where did the pea come from? And they say, well, you can't ask that question. But it started from nothing. Okay, the whole universe started from nothing. We call it the instanton, but don't ask where the instanton came from. That's more or less the answer. Okay, where all this came from, again, I'm going to go quickly through this. It's just the chronology, mathematical chronology of how these notions came to be. Okay, and I'm going to skip some steps here. I'm just going to say, here was Hamilton, and he invented an incredible concept, stationary action, moving while standing still. Okay. Playing baseball while being, fourth, home base or first base or whatever. They have these two notions of motion, static motion, static dynamics, so to speak. It's an oxymoron, stationary action. What do you mean stationary action? No such thing. And the way it's done in mathematics, again, you have to understand this is not the physical notion. They don't care about that. They care about the mathematics of it. And they say if you take the derivative of an itinerary which is short enough, which is in which there is very little to no rate of change, which is what a derivative is. It calculates the rate of change. If there's no rate of change, what you get is 0. So if you throw the ball up in the air and it just stays there for a second until it comes back down, the moment it stays there, okay, you have stationary motion, because all you have to do is take the derivative of that no motion, you could say, and you get a number. It's got to be 0 because it's going to come down. There's no rate of change up there. And that's more or less the notion behind stationary action, okay? Try to visualize it as best as you can. It doesn't get any better than that, okay? Okay, from there you get people like Heisenberg, okay, and he came up with his notion of the principle of indeterminacy or uncertainty principle, whichever one you want. And he said when the ball moves, the ball doesn't stand still, and when the ball stands still, it doesn't move. He had this relation between momentum and position. He says the more you know about one, the less you know about the other. No kidding. Yeah, when I move, I know very little about standing still. And when I'm standing still completely, if I could, completely still, like rigid, like a stone, well, it's very hard to know how much I'm moving. And he got an O for this stuff, okay? And again, it all comes down to this notion of stationary action, of mixing dynamics with static, okay? Why did they have to do all this nonsense? Well, because they couldn't explain action at a distance. So they had to describe it mathematically. And the way you describe it mathematically is and it has to do with the evolution of quantum mechanics after World War II, which is you look at the paths and you say, look, there's this motion, okay? But if you take the derivative of that itinerary and there's not enough rate of change in there, then you can say, you have 0 as far as your derivative is concerned, mathematically. And what that does is allow you to treat that whole thing from a visualization point of view as if nothing moved, okay? Because there's no change in the rate, no rate of change. That's the notion in general, okay? And so one of the guys who picked up on that was Richard Feynman, okay? And what did he do? Well, if you take the classical path integral, you just take a ball going from A to B, and you say, well, it went straight. Okay, we're done, okay? But in quantum, according to quantum, because of the uncertainty principle, the ball, and we're talking about, again, a quantum ball, Okay, so keep that in mind. What was a ball? It's an equation. It's a probability wave or a probability function or whatever they want to call it. It's a number. Okay, but they're going to treat it as a ball. That's where the trick comes in. And what they do is they have this ball that goes from A to B, but according to quantum, because of the uncertainty principle, that ball goes through every possible itinerary, trajectory that you can imagine. It goes through all of them. It's not that it can go, it's that it does go. A particle goes from A to B through all these itineraries, through all these paths. And you say, okay, let's concede that. I don't know what kind of sense that makes, but is that what you say? Okay, and so what's the deal? And what Feynman supposedly came up with, he said, look, we can treat that also as a single integral. And the way they do that is some of these paths cancel out for different reasons, like, you have destructive interference, okay? You have also, you look at the most relevant paths. Again, very selective. They say, well, that one that went throughout the universe, what's the chance? How much does it contribute to our real probability of that particle going from A to B? And they say, well, very little, negligible, infinitesimal. How about nothing? And so they reject those points, those outliers. They just get rid of all that, and they calculate, an integral for that path, and they can come up with what they think is, or what they propose is the wave function, okay, which tells you how particles move in the quantum world, essentially. Okay, so this is where his revolution came in, because what's he really doing? He's going to treat all this, and they do to this day, they're going to treat it as a wave, extended wave. It's no longer a concentrated particle until you measure it. But between that, they say, well, it's a wave, it's a field. And what is a wave? What is a field? Well, it's not like a wave is something that travels. They're going to treat it a little differently. They say it's extended. Where is a wave? Where is a field? Well, the field is everywhere. It's the entire universe. But locally here, it vibrates. And they're going to call that a particle. And they're not going to look at whether it's a ball or anything like that. They're just going to describe it mathematically and say, this vibration here, that's what we're concerned with. This is how much the particle is vibrating. Here's the equation. So they represent the equation with a vibration of a fishnet locally, and they say, well, that's your particle. If you can follow my train of thought, that's how essentially what they're trying to do here. Okay, so they have this field, this localized field, which is a particle, but at the same time the field is extended, or the wave is extended, and it's all over the place. And that comes in handy when you want to explain stuff like tunneling, which is another subject I covered the other day. Okay, here is the notion of tunneling. Okay. And the tunneling, what they supposedly saw or observed, they claim they observed in the lab, is that they pass light or an electron from to a barrier. There's a barrier, an energy barrier, okay? And it turns out that the particle goes right through the energy barrier, is on the other side, and it does so faster than the speed of light. It does so like instantaneously. It appears it's already on the other side of the barrier. How can that possibly? How can a particle go through a wall? Imagine throwing a basketball, like shown there, through a wall, and it's on the other side, but it's on the other side before you even throw it almost. As soon as it touches the wall, it's already on the other side at the same time. That's what these people are saying. And you say, well, that doesn't make much sense. No, it doesn't. And here it is. What they do is they turn the particle into a wave. Or they can turn it into a field as well. They use the wave. And so the wave is already on the other side. The wave is extended. It's already extended on the other side. Okay? So they claim that what they did here is throw a ball, and then they have this extended object that already started at where the ball was, at the starting point of the ball, and it extended to the other side of the energy barrier. So there is no time involved. It's like all you got to do is take an integral there, right? Path integral. And you get a number, and that number is already on both sides, physically. From their point of view, from the way they analyze this, physically it's already on both sides. So that's how they get through this little story. Okay, that's their story. Okay, and here you have another version of tunneling. Okay, how did they do it? These are the steps. If you want to explain tunneling to someone, very simple. You convert the ball into a wave or a field. That's step number one. Step number two, you tell the crowd that the wave or the field is everywhere. Okay, so now you covered all the bases. The player is at 4 bases at once. In fact, they say that, quantum says a particle can be at all places at once, and it is. It's not that it can, it is at all places at once. And you say, how can that possibly be? They say, well, it's the principle of uncertainty. Heisenberg's principle of uncertainty allows for it. In quantum mechanics, it's the foundation of quantum mechanics. Particle is everywhere. And it's also localized. It's only localized when you measure, when you do something to it, when you try to see it or whatever. But otherwise, it's everywhere. Okay, so this is their explanation. So these are the steps you got to use if you want to explain, tunneling to someone. Okay, step number 3, clarify that each ball tracks its own proper time. Every ball carries its own clock. So if you say, well, how come this particle takes a longer route and arrives at the same time as this one, which went straight? Well, that's to you. See, to the particle, it's carrying its own clock. If it goes at the speed of light or close to the speed of light or whatever, it carries its own clock, and you have time dilation, and that relates it to special relativity. Okay, so that's what they like about it, that you can put all this field theory, this quantum field theory, you can relate it to special relativity, and there's a chance of unifying these two theories. Okay, so this is why they like it also. Okay, you apply the principle of stationary action, moving while standing still or vice versa, and then the ball is now on the other side as a wave or a field in 0 time, because the wave is everywhere. Okay. So these are the tricks that they play, and they say, well, mathematically it's sound. In other words, that's what they're going to do. They're going to play with all this stuff mathematically. Okay, and then when they give you the physical interpretation, the physical version, they lost you completely, because that's the part people want to understand, and you won't understand it in the case of quantum mechanics. It's all irrational. Or like Mr. Feynman said, physicists, mathematical physicists, have given up on that. I'm trying to understand all that, trying to explain it or whatever. So they don't deal with that anymore. They consider all that stuff philosophy. That's treated as philosophy. Okay, so let's get to where we are today. Okay, so we have this, the instanton, okay, and you won't find it in it's a particle, right? Pseudo particle, quasi particle, okay? And where do you find it in the standard model of particles? Well, you won't find it in there. In fact, there's a whole bunch of pseudo and quasis out there. I call them quasis because they're kind of quasi, okay? And you won't find them you find all these mentioned out there and people studying them and writing papers in the official literature, but you won't find it in the standard model. So don't look for it in the standard model. You won't find any instanton there, and certainly you won't find a phonon, okay? Okay, and here we have what these particles look like. Okay, there's your classical particle. Okay, I think we all understand that's a ball. You want it a cube, fine, it's up to you. Triangle or pyramid, whatever. Typically, people illustrate it as a ball. What does the quasi or the pseudo particle look like? Well, it looks like that. It's an equation, maybe a wave function. That's the so-called quasi particle or pseudo particle. It's a bunch of hieroglyphics, mathematical hieroglyphics. And what does that have to do with a physical interpretation? We're talking about balls going through walls, turning into fields and waves. Well, it doesn't have anything at all to do with that. The way they do it is they simply say, look, this is the equation, this is the description, and that's what they care about. Okay, here's the definition, I guess you could say, quasi-particle. And collective excitations, that's what they are, okay? They are emergent phenomena. Emergent phenomena. What is an emergent phenomena? I've got a little definition here. Give me a second here. Let me get it up there. Here it is. Okay, here's the definition of what they call emergence or emergent phenomena. For those who are not familiar with this concept, it occurs when an entity is observed to have properties. Properties. They're going to talk about properties, okay, not the entity itself. Its parts do not have on their own properties or behaviors which emerge. That's why it's called emergent. Only when the parts interact in a wider whole. Okay, so that's the notion of the quasi-particle. It's a collective excitation, which is again an emergent phenomena that occur when microscopically complicated system, such as a solid, okay, behaves as if it contained different weakly interacting particles in vacuum. Okay? And here's an example. An electron travels through a semiconductor. Its motion is disturbed in a complex way by its interactions with other electrons and with atomic nuclei. The electron behaves as though it has a different effective mass traveling unperturbed in vacuum. Such an electron is called an electron quasi-particle. Okay? So see, they They have all these emergent properties. And what they're going to do is they're going to treat them as actual particles. So they're not going to talk about the particle anymore. They're going to talk about these properties that emerge when you have a collective vibration or whatever of many electrons, many particles, many atoms, whatever. When they look at the whole thing, they say, oh, a new property emerged. And they're going to call that property a pseudo or quasi particle. Okay, you see how they morph the language. Essentially, you know, what they did was take a concept such as a property of an object, and that's what they're going to treat as a ball, as a particle, as a corpuscle. And they're going to do that throughout their physical interpretation. When you ask them, when you finally put them against the wall and say, hold it, are you talking about particles? Oh, no. In quantum, there are no such thing as classical particles. What we're talking about here is, equations. That's the answer you get. Okay, so what's the deal with a phonon? Well, the phonon is also one of these pseudo-quasis. Okay? And again, they had to create these little particles to explain certain motions of many particles or many electrons or many atoms at the same time. In the case of the phonon, you say, well, why can't we use the same one we use for tunneling or for some of these other things, like why can't we use the instanton there? Why can't we use the same particle over and over and over? Well, they had to categorize all these particles. And in the case of the phonon, this is the particle of sound. Yeah, you heard right. It's the particle of sound. You wouldn't be able to hear if it weren't for the phonon, okay? You say, hold it, what do you mean sound? Well, again, it's a quasi, it's a pseudo, means that they're going to look at the excitation of many particles, in this case, in a crystal lattice. Okay, so you've got all these atoms that form a crystal lattice, say, of a metal or any solid, for example. And they're going to vibrate, okay? And that vibration creates a sound. They're going to call that collective sound a particle called a phonon. Okay? Yeah, you follow me? This is what they're going to do here, okay? So here's the fellow who invented it. His name is Igor Tamm. He's a Soviet scientist, died already. I think that's him because it's the only Igor I could find. I guess he moonlighted in a Frankenstein movie, and so there's your Igor. The concept of phonons was introduced in 1932. Look how far back, okay? By Soviet physicist Igor Tamm, okay? The name phonon comes from the Greek word which translates to sound or voice, because long wavelength, listen to this, long wavelength phonons give rise to sound. So when we have a long wavelength of a phonon, which is what? An excitation of many particles, vibrations, they're going to say that that whole thing is a phonon, and without phonons we would not have sound. Okay, so now the excitations, the properties of objects have suddenly become a phonon, and they're going to treat that as a particle, and they say, well, without phonons you wouldn't be able to hear. So this is where the metamorphosis occurs, where the concept suddenly becomes something that hits your ears or whatever, vibrates in there in your eardrum, something like that. You try to imagine it if you can. The name is analogous to the word photon. Okay, so you have phonon, photon. Okay, see how they came up with all this stuff? A phonon is a collective, okay, many, excitation in a periodic elastic arrangement of atoms or molecules in condensed matter, specifically in solids and some liquids, often referred to as quasi-particle, okay? Why do they refer to it as a particle at all? Why do they use the word particle if it's not a particle? Is it to confuse you so that you think in classical terms, in classical corpuscles? Is that the point of using the word particle, to sneak it in there? I mean, what is the standard model of particles? Are we talking about, is the glue on a particle, is the mu on a particle, is the electron a particle? Or are these just equations? What is the standard model of particles of quantum mechanics? So they use the word particle, which they inherited from classical mechanics. They kept using it because they suggest or insinuate that they're going to be dealing with little balls when they're not. They're going to be dealing exclusively with abstractions, with equations, which when they give their physical interpretation, they're going to morph into particles. They're going to insinuate to you who don't care about the math. You say, okay, give me the bottom line. I want to know how this particle got over there, what the trajectory is, what it did, how it collided. And they're going to say, well, yeah, it's that's when we treat it as a ball. So here they're colliding these things, like in the CERN at the Large Hadron Collider, and they're telling you they're colliding, they're smashing, they use these words, right? Smashing particles, And you say, okay, I understand that. No, you don't, because they're striking equations against each other. And the pi goes this way and the rho goes that way. A phonon is a collective excitation in a periodic, etc., okay, often referred to as a quasi-particle. It is an excited state in the quantum mechanical quantization of the modes of vibrations for elastic structures of interacting particles. Phonons can be thought of as what? Quantized sound waves. Well, there is no physical object called wave. Wave is also a verb. And again, if you look at that transverse wave that they always put since the days of James Maxwell, it's all vectors, mathematical vectors, magnitude and direction. That's all they are. And they put all these vectors moving on the screen. It's very scary stuff, okay? So that's what they are. They're quantized sound waves similar to photons as quantized light waves. Okay, so that's what they do. They reify all these objects. And what did we see at the beginning? That anytime you do a reification of a concept into an object, treat it as an object, well, you're doing some terrible irrationality in the discipline known as physics. Okay, here, so that you can see what how they illustrate this stuff, okay? And here you see a visualization of the phonon, okay? But the phonon is not one of those particles or anything like that. It's what you're seeing, the effect, the excitation, all these of the collective of the whole neighborhood of particles, right? That whole thing is called a phonon. And you would not be able to hear if it weren't for the phonon, what? Particle. So they turn all that concept into a particle, and now they deal with a particle because that's how they do it in mathematics. They get a solution, they say, okay, this solution we're going to call phonon. And now they're going to move that solution around to give you a physical interpretation for what they're talking about. So these are different modes of vibrations that that they came up with, and each one of those different vibrations is known as a phonon. So you got phonon 1, phonon 2, phonon 3, all these different phonons. Okay, great stuff. Okay, so it's fancy stuff. They like to look at these little pictures and illustrate them. They call these collective vibrations phonons. Okay, so that's what you're getting for the money you pay these guys. Okay, that's what they're doing here for you. Okay, let me get this one. Here's another version of this, okay, more or less, so that you can see it. And again, an explanation. Vibrations of atoms in a solid can be treated as elastic, acoustic waves propagating through the lattice. Okay, so you have a lattice, and lattice is like the side of a, or one of the lines that connects two atoms in a crystal. Okay, so you go in there with your telescope, microscope, whatever, you see at the atomic level, well, then what you've got is one atom here, another one there, and somehow that forms a lattice, forms the edge of the crystal structure. And what they're going to do is going to tell you about the vibrations that happen all along this at the subatomic scale. Okay, so the energy of these waves are quantized. Okay, they're turned into a little ball. Okay, that's what quantized means. Quantum, little ball, packet. Okay, because the atoms are discrete quantum particles. Quotation. Okay, phonons are discrete packets of vibrating energy. Okay, there you see it. You say, what is the phonon? A little ball that's going up and down? No, the phonon is the effect, is the motion of all those particles. That motion, that vibration, that's what's called a phonon. Okay, so now you know what a phonon is. You wouldn't be able to hear if it weren't for all them phonon particles hitting your eyes, all those vibrations. Okay, okay, and so what is energy? They say energy, here it is. This is what Nobel Prize Feynman told us about energy. It is important to realize in physics today we have no knowledge of what energy is. Yeah, because energy is not a what. Energy is a concept, and so you can't say what is energy. No, things we point to and concepts we define, and he never realized that. Okay, never was taught that in wherever he went to school. Okay. Okay, and because of this, you get to the next level where you get people talking about types of phonons, like talking about types of shirts or types of pants. Well, here's one fellow who talks about different types of phonons. Optical phonons are excited easily by light. In acoustic phonons, both positive and negative ions swing together. Okay, so there's a physical or pictorial representation of an acoustical mode. How about the optical mode? Well, optical phonons, positive and negative phonons, swing against each other. Okay, so they have all these different categories of phonons, which are simply different modes of vibrations. Okay? So they get to the next level where they start treating phonons not only as particles, as discrete particles, but they began to move them around, categorize them, and do all these fancy things with them. What are the questions you should think about today after listening to all that? Well, these are the questions that I propose to you for you to ponder. Okay, what is a particle? That's the first question. What is a particle? Is a particle, like these people say, a pseudo, a quasi, or a particle is the corpuscle of old, of the ancient world, of the classical world? Is that a particle? I mean, when someone says particle to you, what are you thinking of? Are you thinking of an equation, or are you thinking of a speck of dust, a grain of sand, a little p instanton, a p? What are you thinking of? Well, everybody thinks a particle is a particle, like the little particle that's in your eye. Oh, I got a particle in my eye. That's what people think of the word particle. At least that's my take. I don't know about yours. You might think particle is, an angel, a spirit. I don't know. So, first question, what is a particle? Okay, and second one, does an excitation qualify as a particle? So you have a vibration of whatever. Could be water. Could be the air, for all I care. You have a vibration of something. So that you have a something, you have a bunch of atoms there, they're vibrating. Is the vibration itself, does that qualify as a particle? Can you say that the vibration is a particle? Which is what they're doing with pseudos and quasis, okay? Is a pseudo-quasi particle a particle? Okay, so this is the train of thought. This is my reasoning behind this. I mean, can we treat all this as particles? Are these real particles? Can we talk sensibly by converting vibrations into particles? Vibrations of what? Of energy, which is even worse because you have vibration of a concept. Like saying, oh, we have the vibration of intelligence, we have the vibration of love, and that's a particle? If quantum particles are not objects, things, right? If they are mere concepts, does quantum mechanics have anything at all to do with physics? Okay? What is physics? Is physics about giving you physical interpretations? I mean, these people are just going to give me equations, which are descriptions, and they're going to say, well, we were able to describe something in the lab. Yeah, you were able to describe it, but you're not able to explain it. You can't tell me what's happening in that little world. And one of the problems that comes up with this is what I mentioned the other day, and that's that when you have light interacting with atoms, like with electrons, well, you can say that light and even the electron belong to the quantum world, and we don't know exactly what happens there, we cannot explain it, fine. But when it interacts with atoms, the real world, like light hitting your table, well, you have to explain that interaction. Now you're not talking about the quantum world, you're talking about the interface between the quantum world, the one they can't explain, with the real world, which is the one you see, touch, measure, etc. So now you had a problem because now you have to explain that interaction between the real world and this quantum world which they've invented. Okay? And that's where they run into trouble because they cannot explain that interaction.